Hi there, Spark fans. Rob Reynolds here. We all know that there are a lot of cool people out there doing a lot of cool stuff with our products. Every now and then we'll find something that interests us and we like to reach out and see if we can learn more about it. And that's the case with today's interview. We're going to be talking with Jean Rabault, who is a senior engineer at the Norwegian Meteorological Institute. Now, they've been using the Artemis Global Tracker to track the flow of sea ice through the Arctic. It's incredibly cool, and we're going to learn more about it with him.
Jean, why don't you introduce yourself? Tell us a little bit about yourself and about your organization.
Okay, yeah, so good morning or good evening from Oslo. So as you say, my name is Jean Rabault and I'm working at the Norwegian Meteorological Institute. I've been working there for about a year and a half, and before joining MET, we call the Norwegian Meteorological Institute for MET very often. So before working at MET, I was working at the University of Oslo on both my PhD and my postdoc, and working on relatively similar topics. So on many aspects, my work at MET is a continuation of my work at University of Oslo, which we usually call UIO. And what I've been doing is a mixture of different topics, of course, but one of the focus points I've had is to study the interaction between ocean waves and sea ice in the polar regions, and in particular, of course, in the Arctic, because Norway has a specific interest in the Arctic, but also in the Antarctic with some colleagues from Australia. And I think what we discovered quite quickly, my supervisor and myself, when starting to work on this, actually quite a few years ago in 2015, is that there are many people who are very smart and do a lot of advanced mathematics about those problems of wave-ice interaction. But really, I think in order to make the operational model better, what we need is much more in situ observations gathering. And this is expensive and this is difficult to do. So in addition to the scientific part, we've had more and more an activity about also the development of instrumentation and the tooling part. And this also is a very good fit for the Norwegian Meteorological Institute where I'm working now, because MET has some core responsibilities about providing some weather, and it can be like atmospheric weather, ocean waves, it can be sea ice, drift maps and stuff like this. So this kind of weather forecasts to be used by other actors of the society, and also conducting some research about the evolution of climate, and so a specific interest also for sea ice from a variety of point of view, from the theoretical stuff of just understanding the coupling with the waves to the operational questions of being able to have better weather forecasts, for example.
Great, that's great. That's so cool. So can you tell us a little bit about this project in particular and what inspired it?
Yes, so in this project, we're very interested in looking at the closed loop interaction between ocean waves and sea ice, because actually the sea ice is a strongly coupled system with, for example, the ocean and the atmosphere. And I can give like two small examples of coupling. Like there is a coupling with the albedo effect. So when the sea ice extent gets reduced, you have more areas of open water, of course. And for example, sea ice will reflect like around 70% of the incoming sun energy back, while the ocean will absorb about 90% of it. So it changes a lot, really, the heat flux that you have in the polar regions. And another example of coupling, which is even closer to what we are doing, is that the Arctic basin is kind of closed. And for example, 20 years ago, the whole area was covered in sea ice for a wide part of the year. And then you don't have much space for ocean waves to develop. But now with the reduction in the extent of the sea ice, you have quite large regions of open water for a much longer part of the year, where you have enough space for the wind to create quite big waves, and then those big waves meet the ice, break the ice, and then as a consequence, the ice melts even faster. So really in this project, what we want to do is to generate increased volumes of in situ observation in order to help my colleagues in another department at MET develop better coupled ocean, atmosphere and sea ice models. So what we do basically is that we join cruises of icebreakers. In particular, there is a new icebreaker that was put in service a few years ago in Norway, and then deploy our instruments to gather as much data as we can.
That's great. That's really cool. So what are the top 3 requirements for this project? What were the have-to-haves for this?
Yeah, so the first thing is it has been traditionally expensive and risky. I mean, not in the sense of risk for human life, but in the sense of you never know how much data you get to gather those data, because we're in particular interested in an area that is called the marginal ice zone. So the region that is really at the interface between the open water and the thick pack ice. And this is a region where the ocean waves are going to break the ice, and yeah, where the coupling will be the strongest. And it's also a very dynamic region, right? It's a region where if you have a storm coming, everything may break up. If things break up, then you lose your instruments. It's also the region where you have a mixture of like open water leads and ice flows. So for example, there is a lot of polar bear activities, and these polar bears are known for eating and destroying and chewing instrumentation. So really, traditionally, it has been a bit scary as scientists to put instruments here, because you may pay like $20,000 for an instrument measuring sea ice drift and wave activity, and you don't know if it will last for a day, a week, or a month. So the first requirement for us is to have an instrument that is able to do a bit the same kind of measurements as a usual commercial instrument, but maybe 10, 15, if possible, 20 times cheaper, because then we can deploy these en masse, and if some of them die quickly, I mean, it's not a big issue. So really, I think the cost is one of the main motivation for going to the solutions we do. In addition, of course, we want to have time series that are as long as possible. And this put constraints on the energy consumption, because I mean, we can have temperatures of minus 20 degrees. So a lot of batteries don't have so high performance in those conditions. In addition, there is 6 months of polar night. So solar panels don't give you much input for a wide part of the year. So we are really interested in getting the power consumption down so that we can avoid spending thousands of US dollars on batteries and having huge bulky instruments. And this is another place where like the Artemis Global Tracker was very attractive, because we really managed to cut the power consumption by between 2 and 3 orders of magnitude compared to what we had before. And then the third requirement, of course, is that we want something that is like both easy to assemble, open source, and we know what kind of data processing is going on. So yeah. To have, like, as a scientist, we like to have full insight into what the instrument we are using is doing.
That's great. So I think you touched on some of this, but why is the Global Tracker, why did you choose the Global Tracker for this project? Power consumption seems to be a big one.
So I can start by 2 seconds of history, maybe. So we've been doing this for quite a few years, this activity. So in 2015, we actually went to the field with some instruments that we had to collect afterwards if we wanted to have any data. So it was basically based on some MOXA industrial computers coupled to some VN100 IMUs. And it was really a mess. I mean, we had huge lead acid batteries, and those lead acid batteries, even if they are 0 degree and minus degree tolerance, they actually only survive those low temperature when the charge level is over 80%. So as soon as you start to deplete them, they freeze also. So we got actually a lot of nice data and some papers and some understanding out of it, but it became clear that we needed something better. So in 2016, we came back, and I had developed in our lab some very simple pure logger solutions. So it's just basically an Arduino Mega and a GPS breakout, and still logging this VN100 IMU on a SD card. But then it's still a bit frustrating, right? Because we need to collect the instruments, and if the ice breaks and moves away, we lose the data. And this was more or less only possible to use like in land-fast ice in fjords in Spitsbergen and Svalbard. So in 2017, we came back again to the field, and this time I had developed a home instrument with, in addition to this Arduino Mega logger, I had added a Raspberry Pi in order to do the processing, and a small Iridium modem in order to do in-situ processing and send the processed data that are actually quite small through Iridium. And this instrument actually worked quite well. The design was released. We shared it with people in Australia, but I mean, it's quite a bit of work to build. It costs quite a bit of money, and the battery autonomy is good, but we need big batteries. And so I was very excited when I saw the Artemis Global Tracker come, and first, it's much smaller. I mean, instead of having a big Pelican case, I'm able to pack all of it in a small enclosure. Second, it's actually quite a lot cheaper than the solution we had before. It's also much less work to build because it's a lot of the tools we need on the same platform, right? We have the Iridium modem, we have the GNSS, we have a good microcontroller, so we don't need a Raspberry Pi for doing that signal processing any longer. And then, of course, the power consumption was much, much lower, which is also very attractive. So I think it just improved on absolutely all the criteria we had compared with the solutions that was here before. And I think this transition from having a microcontroller for doing the logging of the data plus a solution a la Raspberry Pi for doing data processing, and instead going to a pure microcontroller solution because the microcontroller is powerful enough to take our Fourier transforms in situ and everything. I think we are among the first who do it. So as far as I know, for example, commercial instruments have not yet done the transition, but I think they will because there are so many advantages in it.
And I think that's a huge part of what we here at SparkFun love about open source. We can put something out there and people around the world can take it and improve on it and make it better and make it fit their needs. And that pushes the technology, I think, faster than proprietary stuff out there, commercial solutions, which I like.
I definitely agree. Yeah.
Great. So,
and we see this nice interaction with SparkFun too. So for example, the Artemis Global Tracker, as far as I understand, was originally developed in order to be put in high altitude balloons. So actually the size was an important requirement. It should be as little and as light as possible, while we don't care so much about an extra centimeter here and there. And what is more important for us is to have more pins broken out in the PCB because maybe we want to add a pressure sensor and a temperature sensor. So I actually was a bit in dialogue with SparkFun, and I heard that there is a new version on the way with, like, they managed to squeeze a few extra broken pins on the PCB here and there. That will be very good for us.
Good. I'm glad. So for you or for the Met, what is the biggest benefit of this project? I think you've named several, but what's the one thing that was like, this is what we have to have for this project?
So I can give 2 or 3 elements of response here. The first one is that for the same budget that would have allowed us to measure like 2 or 3 trajectories in the sea ice, we were actually able to measure 13 trajectories in the sea ice. So it's quite a bit more. And next time it will be even more. It's because, like, you know, when you start building this stuff yourself, you have some fixed cost, like buying a soldering iron and buying an epoxy tube gun and this kind of small equipment. The other thing is that the instrument we would have used otherwise, it's, for example, this SOFAR spotter buoy. That is a very nice instrument on many aspects, but like in the Arctic, without solar input, it only lives for a couple of weeks, while our instruments live for like up to 6 months on just 2 D-cell lithium batteries. So it makes a huge difference. And also, for example, the commercial instrument we're thinking about is using GPS in order to measure the wave displacement. And this is convenient in open water where the waves are quite big, but in sea ice where the waves can go down to just being a few centimeters, it's actually not accurate enough. So we can see that the noise threshold of our homemade solution is actually much better than at least the specific commercial instrument we're initially thinking about.
Cool, great, cool. So yeah, this is all fascinating to me, and I'm sure to many of our viewers out there. I know that sea ice melting bad, being able to track it and figure out why it's happening, what's happening to it is outstanding, and that's what you are doing up there. So I believe you released these back in February, is that right? It's November now, so
yes,
9 months-ish.
exactly.
So what are you hoping to achieve both in the short term and the long term with these?
So in the short term, we have gathered a number of drift trajectories. We have validated the design. We have colleagues doing numerical models development who can use the data we have gathered to calibrate like their models for sea ice drift and sea ice and waves interaction. On the long term, we we really hope to be able to kind of help create a community that is focusing on using open source for geophysics in field measurements. Because it has a lot of advantages, like having a reference implementation for many of the measurement instruments, and being able to cut costs, being able for new groups to join the gathering of data with a very low threshold. So I think for now, this is like really the meta objective that goes beyond just the gathering of data. And I think we've had quite some success about it. So the instrument from 2017, actually, the design was picked up, as I was naming, by some colleagues in Australia. Now this new design that we call the V2021, we are actually developing it together with the same colleagues in Australia, and at the same time, some colleagues in Japan have been participating heavily in it. We have some colleagues in Canada who are also involved. Some people, some colleagues in Alaska, University of Fairbanks, are also following quite tight on the development. And even at Met, for example, I'm from the Oslo division of Met, but the people in Bergen town in the western part of Norway are starting to pick it up too. So I really think that there is a lot happening there. In a sense, I think it's really great what you're doing at SparkFun, because you're making this electronics available for everybody. And like the same way, like in our community of numerical weather forecast and climate study and stuff like this, you would never think about paying a private company for buying a model from them, because all the numerical models are developed by the communities, by the scientists, available. And this is possible because we have had good compilers for a long time. It has not been too difficult technically. I mean, even if there are plenty of challenges in practice, but it's possible for people to code numerical models and deploy them on supercomputer. And I think that for the measurement parts, it wasn't possible to develop instrumentation without having some guys with PhDs in electrical engineering and computer science and so on 10 years ago. But now, I mean, I don't have a background in electrical engineering at all. I just learned from open source communities, and I was able to develop this. So really like making it much more accessible to people who are not specialists for 10 years studying electrical engineering.
Thank you. Yeah, that's an important part of what we feel we do here. What we do here is, there are people with brilliant ideas that don't have $1 million budget. But if we can get the tools out there for everybody to get their hands on, these ideas are going to blossom, and they can only help the communities. Right. So, so what type of impact do you see this having for not only your organization, for MET, but also for the greater oceanography community?
Yeah, I think the impact is being able to gather at fixed budget, constant budget, much larger volumes of data. And this has a lot to say for, yes, the numerical models, the monitoring of the oceans. And actually, we are not at all the only one having this idea. For example, DARPA is having a project now about, I don't remember the name, but something like Ocean IoT or something like this, and saying exactly the same. They want to award some contract to companies, and the requirement is being able to build drifters quite alike what we are able to build for about the price tag we are now able to build. They put also some requirements about being able to produce like 6,000 per year. I won't be able to produce this in my garage, but that shows that there is a broader awakening that this is now made possible. And I think really this is the direction, not only for MET, not only for the studies of waves in ice, but also for lots of domains in oceanography. And you can think also for operational users, like to save lives. So for example, I was discussing this. I mean, this is internal to MET, but applicable at other locations too. But discussing with some colleagues who are in charge of models for drift, that the kind of model you would use if a boat sinks and you need to look for people. And they were saying like, it's super nice because like those things, those Iridium and GPS drifters are so inexpensive. You could just send a plane and then throw 20 of them in the area, right, to follow the drift of those things in real time, for example.
That's great. Yeah, and that's part of what we like to do here. We just make a thing. We have no idea. We can come up with 100 ideas of how to use it, but once it's out in the community, 1,000 ideas are going to come back at us. And I think that's super important as well. So looking ahead, what do you see or what do you want from this project? And honestly, how can we, SparkFun, help you to achieve that?
So from the scientific point of view, we want to gather these large volumes of data, and I think we are well on our way. And also our partners in Australia and Japan and Canada and the US are also benefiting from it. From a broader perspective, I think, I mean, we are users, right? So we are always happy to have microcontrollers that uses less power and has more computational power, of course. But I think we're already in a very good place now. So maybe we will consider when we really, because it's always the same, like, you want to build something and then you have to build the first version to really understand all the intricacies of it. And I think maybe now that we start to really understand exactly which part we need, maybe we want to have everything on the same board and find a way to produce this together with SparkFun, for example. So we are trying to discuss a bit with our colleagues and understanding, okay, those drifters and wave measurements instruments, do we need like the 4 or 5 groups putting our efforts together? Like, do we need 100 of them? Do we need 150 of them per year? And then is it worth to have a dedicated board, not just the Artemis Global Tracker on which we add stuff, but really a dedicated board for doing it? Yeah. So for example, for our case, we have the Artemis Global Tracker. And since we have long-term deployments in conditions with quite cold temperatures, we cannot really trust that the voltage of our batteries is very stable. So we need to have a small step up, step down boost converters that we buy from Pololu, colleagues of yours also making open source who make very good power regulator. In addition, we want to measure for this wave motion. And for this, the best solution we found was actually not to use a dedicated IMU, but to use a dedicated 9 degree of freedom breakout. So something that only measures acceleration, gyroscopic rates, and magnetometer data, and does not do the processing on the chip, because this way we can do the processing in real time on the Artemis chip. It's powerful enough to run the computations we want on the fly, and we save a lot of power. And the design also, we have more control about the kind of code that is run. So maybe in the future, maybe if there is a market that is big enough, putting all those components on the same board so that a user who really have no idea whatsoever about electronics can just buy it and is ready to go. That could be something exciting.
We will definitely keep that in mind. The more we hear from users, especially users who want many things to gather data points all over the world, the better we can adjust.
Yeah, and I think that there are some points that are quite general. I mean, the use of a 9 degree of freedom measurement sensor instead of using an IMU. I mean, I think when the Artemis CPU is strong enough to run the Kalman filter on the fly, really it's something general, right? You don't really need to have a BNO08X or another kind of IMU that uses like 35 milliamp instead of using 7 milliamp, right? And that may be a bit difficult to talk to when you can do it yourself. And I think it's the same for the power regulator. I mean, power issues is always a mess when you try to deploy something in the field with varying temperatures. So really having a small piece of circuitry that is able to take any input between 2.7 volt and 11 volt and give you a stable 3.3 volt, and you never need to think about it anymore. It's really like a luxury that we cannot live without any longer, in a sense. Mm-hmm. It's the same thing, like we don't need to be worried that, okay, if the Iridium modem pulls out 250 milliamp during a burst, is the voltage of the battery going to drop? Because yes, the voltage of the battery is going to drop, but the step up, step down is going to take care of it for us.
Great, that's cool. So I believe you said you have one tracker that's still sending data over 9 months it's been?
Yes, exactly. So we have one tracker that was deployed in February, and then it worked on the sea ice very well for a month or so. And then we had a little issue, which is that, as you see, like the boxes we use, typically they are quite low profile. And I mean, this one is orange, but we would never paint it orange when we put it in the Arctic. It's low profile because we don't want polar bear to find them, choose them, and put them into pieces. But the problem then is that yes, being low profile means that they are less visible, but it also means that if there is a big snowfall, it gets covered and we lose the iridium and GPS transmission. So this is what happened to this instrument. It got buried in the snow for a month or a month and a half. And then when the snow and ice melted, I mean, it came back to the free atmosphere and was able to transmit. And it transmitted for a few weeks from the sea ice before the sea ice melted completely, and then it just drifted in the open water. So it drifted all the way from the coast outside of Svalbard, Spitsbergen, to a few tens of kilometers outside of Murmansk. So apologies to our Russian friend. We never intended to go to Murmansk with our instrument, but we didn't really choose. And the only thing that was on it was a GPS and an IMU. So there is nothing shady about it. And now it's on its way to Nova Zelmia, also like the other side of the small basins there. So I think it's a tribute to the fact that it's possible to write very robust code. I mean, if you put a bit of watchdog safety in a sense, even if once in a while there is a bug and something crashes, it just reboots very nicely. It's also a confirmation that the power efficiency is very good because we just have 2 D size factor lithium cells in it. And it's an early instrument, so it doesn't have full wave measurements, but for example, it's measuring GPS position each 30 minutes and transmitting it, so it's still quite a lot of iridium messages. And actually, we have a joke I'm going with the colleagues I'm working with on this because, I mean, we didn't expect to have such a high degree of success for this first deployment test. So we didn't implement a two-way communication to be able to reduce the frequency of the messages. It means that we use actually quite a bit of money. It's about maybe $150 a month in iridium communication. I mean, on the new version, we have just implemented a two-way communication so that we can reduce the frequency of the GPS or wave data if there is not too much interesting happening. But so what the colleague was saying is that he is quite convinced that several other of the instruments we put on the ice are actually fully alive and transmitting, but he just does not want to activate the iridium subscription because it would be too expensive.
That's great. Well, thank you. Is there anything else that I may have, as a layman, not thought about to ask? Anything else you want to share about this project with us?
No, I think you covered very well the different points of questions. So,
well, thank you. Thank you so much for your time and for this information, your knowledge. I really appreciate this.
Yeah, thank you very much for inviting me to talk about it. It's always a pleasure, and I hope this can invite what's the word for it? Inspire several other groups to look into those possibilities of open source instrumentation. And I mean, we're still working on the draft that explains all our design and validates it against commercial instrumentation, because we did one deployment recently where we have both a commercial instrument and our instrument to see that they do the same kind, produce the same kind of statistics. But we hope that it will be all published, both the validation data, the paper, and the code as open source in the course of early to mid 2022.
It's great. Well, I'm looking forward to it.
So, we are not software engineers, and I mean, I spent between 5 and 10% of my time max on this because we have so many other projects. So it's not the highest quality code base ever, but I think it's a good, I mean, you have first to see, is it really possible to do it? And then which features can you add? And then when you have the overview of all of this, you can have a nicely engineered system the next time you design it, which is something we want to do. And yeah.
Good. Great. Well, thank you so much, Jean. It has been an absolute pleasure. I love learning about this, and I can't wait to see what you all do in the future.
Thank you very much.
All right, I thought that was incredibly fascinating and very cool. And the fact that they're working with scientists from 4 other countries around the globe makes it even better. I want to thank Jean again for his time and expertise on this. And of course, we always love hearing about cool projects. If you've got something you're working on, we'd love to hear about it. Reach out and let us know. And until next time, stay safe, be kind, and happy hacking.